So I'll start this session with a question. Raise your hand if you're using generative AI or exploring generative AI personally or at workspace. So I see a lot of hands getting raised. The second question, are you familiar with chaos engineering? All right, that's good. So you're in the right session. Generative AI is affecting and evolving every role in IT industry, and SRE role is not untouched with it. When we think of SRE role, part of the responsibility is to make sure that reliability of the systems are there. And one of the ways you can ensure that is through resilience testing and chaos engineering. And when we think about chaos engineering, there are three key aspects of it. One is forming a hypothesis or assumptions about an application that you want to test and validate. Second is creating and running an experiment to that effect. And third is verifying that you proved your assumptions about the application. Now, when we think about all these three aspects, running and creating and running experiments is rather easier than the other two. What we have seen most of our customers struggle with is forming a measurable hypothesis, and second, verifying the hypothesis. And to solve those two problems, we are going to walk you through a solution that you can leverage to overcome both these challenges. My name is Saurabh Kumar, and I'm a senior solutions architect at AWS. I'm also a member of a technical community that focuses on helping customers on resilience and chaos engineering. And today's talk, I'm joined by my colleague Ruskin. What do you?
Great, thanks, Saurabh. So good afternoon, everyone. I'm Ruskin. I'm also a solutions architect at AWS, been there for about 4 years. So let's get started, right? So we are both AWS employees, just to put it out there. We are going to present concept using first principles, right? So we are going to be using some AWS services, but by all means, it's not necessarily bound to that, right? So take away the principles and you can apply anything you like to it, right? There are different tools out there, different LLMs out there, different cloud providers. So use your service of choice. So today we're going to talk about challenges, right? So Saurabh talked about it's very hard to come up with a good hypothesis, and it's also hard to verify that hypothesis, all right? So we're going to talk about why it is hard. Then we're going to take you through the steps of how do we actually create a good hypothesis, right? So dashboards, metrics, alarms, all the good things we've been hearing about all day. And then pass it back to Saurabh, who'll take you through verification of these, right? Because that's also quite difficult. You have a lot of data. How do you go about doing that? And eventually we'll show you some results, right? And these results are just from a couple of applications that we have created. By all means, it's not the holy grail. You can choose your poison. Whatever application you have, choose your prompts. The verification results will depend on your actual application, right? And we'll talk a little bit about that too. So in here, all of us will fall within these buckets at some point in time, right? We're all users of a system. We are all at some point in time are SRE engineers. We have worn that hat. And we are also backend engineers as well. So we have heard a lot of users come up to us and say, my site is slow. We hear that all the time. No extra information given to us. This page isn't loading. It could be my fault, right? The users often blame themselves. It could be the internet. It could be the ISP. As a site reliability engineer, you often go and look at the dashboards and say, hey, there's no extra load. I can't see any problem. Or all dashboards are showing green. What could be the problem? Or I see some errors, but not really related. And on the backend side, you could be thinking about, I haven't made any change for a week. Where is the problem coming from? Or you go away and say, let me check. And you don't hear from that engineer for weeks or months at an end. Or you actually go and check and everything looks okay. So it's quite a difficult problem. What we have also heard from a lot of the users and customers are unrealistic expectations. Users come to us and say, I want the site up all the time. I want this working with 99.99% SLAs, right? And sometimes it's not quite real to achieve that because there is no real why behind it. We also find that there's a lot of negative sentiment when things go wrong or when things go slow. Never have I had a customer who's happy to come to me and say, hey, my site is slow. It never, ever happened, right? So there's always a negative sentiment attached to it. And what this results in is a forced change. And we want to move away from that, right? So let's re-architect the entire database layer because my database queries are slow. Let's rewrite the front end in a different framework because my Vue JavaScript framework is slow. And we see a lot of knee-jerk reactions. So how do you avoid that? So bridging the gap, we want to move from our usual engineering loop, which is shown on the left-hand side, where you identify a problem, you resolve it, you verify it, you get some kind of steady state, and then there's unplanned stress, right? to a more known state, which is where chaos engineering loop comes in, right? Where you improve on something, you have a steady state, you plan the hypothesis to share how does the system behave? How do you want it to behave? You run an experiment and then you verify that hypothesis, right? And there's a great talk in reInvent, which is our flagship event. And if you want to go through that talk, please do. But there is a virtuous loop around this, right? Like a flywheel. And it's a whole topic, like it's a whole hour conversation. So we're not going to dive a little bit deeper and dive into that at all. We're just going to be talking about two main things, which is planning the hypothesis and checking and verifying the hypothesis. So let's dive in. So we assume that you have a steady state. We assume you have an application, right? We're not going to be writing an application right now from scratch. Let's assume that. But what we're going to do today in the talk is understanding how do we actually create a hypothesis and how do you plan for it? Then we're going to assume you can run an experiment. So an experiment could be anything where you bring the system down. For us, we're going to be showing you AZ impairment, where an AZ goes down, like a data center goes down. Then we're going to show you about how do you actually verify the hypothesis you created in step 2. And then finally, we're going to assume again that you have some tools and steps to improve that application. Right? And all the things we talked about today, the whole day around different topics. So let's dive into steady state. To understand steady state, we need to understand user behavior, right? How are you interacting with the application? We need to observe with dashboards and alarms, etc. And we need to understand our system. Is our system deployed across multiple regions, across multiple availability zones? Do we have a reader and writer database? We need to understand all of that. So this is a steady state architecture diagram. Again, don't read too much into it. It's just an architecture diagram. The key being there is a diagram or some kind of architecture you can rely on. This is a steady state dashboard, right? So again, don't worry about the metrics, just making sure that you have some kind of steady state captured in a dashboard somewhere, right? The metrics are important, but not as important right now. We'll talk a little bit about what metrics are there and how LLMs help you with that. And this is another application called PitSite. So we are going to be leveraging this in our hypothesis generation and verification. Again, the important thing is that we have an architecture, and this architecture is different from the one you saw earlier, showing you that what we are proposing works with multiple different architectures, different dashboards, etc. And this is a steady state dashboard for that architecture, right? So we have that as an input. So let's go down to planning a hypothesis. We've just established a steady state. So creating a hypothesis is hard, right? We don't know what we want to prove out. We often go in quite blind. We want to know what are some of the metrics or some of the thresholds we want to use. We have lots of options. We heard earlier from one of the attendees that I have hundreds of dashboards. I don't know which one to look at, right? And that's quite applicable here as well. Or sometimes we have a dashboard, but we don't know what thresholds we want to use, right? Where is that red line we want to understand and alert on? So we are offering that a dashboard with a steady state and an architecture diagram will give you a good hypothesis. So where does large language models and generative AI come in here? Large language models are really good at understanding large amounts of data, right? So they are good at understanding your dashboards, all the metrics you have on display, also your architecture diagrams, right? You could feed it one architecture diagram or hundreds, right? It doesn't matter. The large language model should be able to decipher that and do all the calculations and crunching on your behalf. Same with the dashboards as well. So the equation you saw earlier, where you have a dashboard and an architecture giving a hypothesis, becomes something like this. You have a dashboard, you have an architecture, and you have some prompts. And you feed it into a large language model, and it should give you a good hypothesis. And we're going to explore that a little bit. So we designed a system prompt, right? What the system prompt here has in detail is not relevant at this stage because the system prompt should be able to be malleable enough for you to change according to your requirements, right? But the key things here are that you need to establish a clear persona. You need to give it some clear principles on what to do, a clear structure. How are you going to actually get the hypothesis coming out, right? What scientific methods are you going to follow? A clear directive. What do you want analysis to focus on? And finally, what does the output look like, right? So if you have these principles in a system prompt, you should be able to get a good hypothesis out by using a large language model. And then the user prompt becomes quite easy, right? The user prompt becomes something specific to the architecture on which you're creating that hypothesis. In my case, I've deployed the architecture in AWS, so I want to see a multi-AZ setting. So I've got the user prompt quite simple because my system prompt is doing all the heavy lifting. So what does it look like in code, right? So the first step you want to do is you want to have an array of content items, right? Because you want to pass in all those architecture diagrams, dashboards into the large language model. So that's essentially what we've done. We capture it all, we convert it into a byte array and pass it in there. And we pass it in the user prompt and the system prompt as need be. So just remember that we haven't really worried about the context length here, like the number of tokens and things like that. So if you're doing it in production or in practice, that needs to be considered as well. You can't pass it an indefinite amount of files because you'll be hitting the token limit. Next, we just instantiate a large language model. In our case, we're going to be using Bedrock. Finally, you get the response out by calling a convert stream API, right? So essentially, as you get hypothesis out, you want to stream it to the end user to make that experience a little bit better. In the request parameters, you're essentially telling it what model ID to use, what the messages are going in, and some hyperparameters if you need to tune the large language model at that point in time. Finally, you just got to iterate through the responses. So it is that easy, right? So the key things are the system prompt and the user prompt and those dashboards and the architecture diagram. And this is what we get out, right? So this is a generated hypothesis. If you notice, it's got clear metrics, right, around what should be the number of requests per 5-minute window. What is the success rate across your services? What is the recovery time? It's got very clean, defined metrics, which are coming from the dashboards you provided and the architecture diagram you provided, right? So it's very bespoke to your needs. It's got a clearly defined steady state. It's got clearly simulation instructions, what you need to simulate, clearly defined expectations, and clear exit success criteria, right? Because that's just as important when you prove out an hypothesis. So what we have covered so far, steady state and the hypothesis. I'm going to pass it on to Saurabh to take you through how do we actually run an experiment and verify it.
All right. So to run the experiment on AWS, you can make use of this managed chaos engineering service called fault injection service, or FIS for short. This is not the topic for today, so I'm not going to go deep into it. But one thing I would call out here is the experiment template, which is the blueprint of the experiment that you are creating. And the other thing I would call out is the experiment report that is generated at the end of the experiment. And this is what it looks like. So it has all the details about the experiment. It captures the steady state. If you see in the screen, on the left is your pre-experiment steady state. In the middle is the experiment state, demarked with a time and shaded area. On the right is your recovery state. So this data is all coming from the steady state dashboards that Ruskin had walked you through before. And it also has all the, it also has all the details about what fault actions were injected and what were the start and end times of that. So FIS or any other mechanism of running an experiment. All right, so now you have run the experiment, and let's talk about verification. Why is verification challenging? We have heard it in the morning, too many dashboards. So because your data, your observability is dispersed among multiple observability dashboards, or worse, multiple observability tools, it becomes very difficult to correlate between the events when you were running the experiment. And because of that, the analysis and the hypothesis verification becomes tedious and time-consuming. To help you overcome this problem, what we propose is this. We take the FIS experiment report, or any other experiment report if you're not using FIS, combined with any additional observability metrics that you've captured in other tool or logs or any other screenshot that you're capturing about that application when the experiment is being conducted, and come up with a prompt and feed all that input to an LLM and let that LLM do the analysis for you, verify the hypothesis for you, and come back with the insight in seconds instead of you doing it manually for hours. So that's our approach. Now let's talk about a prompt. Again, along the similar lines that Ruskin had pointed out, that we are following a structure of the prompt where we provide the initial context. What is the experiment? What is the hypothesis? Again, this is the hypothesis that we had generated previously. And the second section is adding the observability reports. The third section is output. How do I want to define the output to be? In my case, I want this output to be in a JSON format so that I can take it and create a Jira story for tracking purposes. So I said my output should have a title, it should have a result, it should have a description and analysis of why LLM thought that the hypothesis was verified or not. And lastly, any recommendations that LLM has. And the fourth section is about instructions. So a couple of instructions I have given here is that just give me the output in JSON format. Do not append or suffix any extra information. And base your analysis solely on the data that I'm providing and do not make any other assumptions. So it's a structure, some structure to follow. Now, the code snippets are similar to what Jason had pointed out. So I will go quickly. What we are doing here, you don't have to read it. What we are doing here is replacing the placeholders in the code with the actual values of hypotheses and other details. And here we are just appending the evidence that we have collected so that it can be passed on to the LLM for analysis. And lastly, this is where we are invoking again the Bedrock Converse API is helping you to invoke the LLM and do the analysis. Now let's look at the results. So in this case, this is an example where we are based on the architecture, pet site architecture that Ruskin had showed. And this is based upon the serverless components in that architecture. And the experiment we did was Lambda invocation error. And let's see what the hypothesis was to begin with. Here's an hypothesis, and this is what we have seen many organizations at when they're starting with chaos engineering. So this is a good hypothesis, but it does not have any measurable metric or any thresholds. So it says that it would not be significantly impact, but significantly can mean anything. There's no quantifiable threshold to it. Similarly, it says experience will remain consistent, but again, not measurable. So regardless of this, what we did is we took this hypothesis, captured the evidence when we ran the experiment, and fed it to the verification. And this is what verification comes out. It says that hypothesis was not verified based upon the data that you provided. And again, here, two things to call out. The verification can run independently of whether you generated the hypothesis or it was a hypothesis that you started with. For it, there should be a hypothesis and there should be an evidence to analyze. Just like hypothesis, it says it was not verified and it gives the reason there was a noticeable increase. You see, noticeable. It's not like what it was. Was it 100 errors? Was it 1,000 errors? Similarly, this suggests, so it's not based upon the data or the threshold that you defined. Now, from this, let's look at another experiment using a generated hypothesis. And this hypothesis was generated using the code snippet that Ruskin had walked you through, again, based on the same architecture, but you can see the difference here. It is using the metrics which were present in the dashboard. And it is also using measurable thresholds like API gateway latency remains below 2000 milliseconds, or there are 0 errors. So these are the things that LLM picked up from the observability dashboard as a thresholds, and now they're part of your metric, part of your hypothesis. When we give this hypothesis along with the same evidence, this is the result we get. Again, hypothesis is not verified, but you see the data. That it noticed that the latency exceeded by 2 seconds, which breached the hypothesis. Again, errors were recorded, which is not a 0 count. So you see the verification happened, but this time it is based on the data that you specified in your hypothesis. And to show that this process works for different kind of architectures, we did the same process for same pet site application, but it was the other pieces of architecture which were deployed on EC2, EKS, and they were running in multi-AZ setup. So this is again generated hypothesis, and in this case, it is also using relevant metrics along with measurable thresholds. For example, response time is below 100 milliseconds, and the database connections remain steady above 5. When we ran the experiment, collected the evidence, and fed it to the verification, here's the verification result. Hypothesis was verified. And why? it lists out the thresholds that were not breached in this case. Like the response time was still below 100 milliseconds and database connections were stable. So the point here is that both in hypothesis generation, if you're generating the hypothesis, using the dashboards, it is picking up the relevant metrics, relevant thresholds. Same is being used in verification. So you're LLM is quickly doing the analysis quickly and supporting it with the data that it is picking up from the observability dashboards. Now, we'll share some of the best practices that we followed and we think are generally applicable as well. So I'll start with observability. As SREs, as engineers, we are very familiar with system and application level observability. We say take it one step further and start thinking about the user level observability. And in some of the talks, we had heard about real user monitoring. So real user monitoring is a way where you can start thinking about observability from your end user's perspective, what your users would be seeing on your website or an application. But you can take it further and start thinking about observability at the business level. For example, if you are a retail system or an online system, a business metric could be number of orders per second or per minute. Take it further and translate that into a real dollar value, what those 10 orders per minute or per second means in terms of business. So that gives you clear business KPIs that you can plot on an observability dashboard to show you if this experiment were happening and if it was a real manifestation, what would be at the stake. So that's best practices from observability perspective. Similar best practices from prompt engineering perspective. As when we were walking through the prompt, we were showing that be specific, be clear in terms of what you want the LLM to do, and let it follow a structure, like all the input is structured in the one section, output in the one section. And also, whenever applicable, use the prompt-specific constructs, XML tags. Some LLMs prefer XML tags versus JSON format. And lastly, provide helpful context, helpful information, and examples. In some of the cases in hypothesis generation, we gave an example of these are the metrics and these are the thresholds, so LLM can follow along your guidance. This is how we summarize our talk today, and this is a reference architecture that we want you to walk away with. This is very high level. So in generation side, left-hand side is generation where you are providing all the logs, architecture, observability dashboard data to an LLM, let it generate the hypothesis, run the experiment, and then use LLM along with the evidence to analyze the results for you and do it in quick amount of time. With that, we are coming up for questions. And while we take the questions, I'll pull up this feedback survey. This is just 3 questions, would take 30 seconds or less. It will help you design these talks better for you. All right, questions.
Awesome. Really interesting talk. One thing that pops up in LLMs and like machine learning model training is that you will have the output go back into your data and potentially poison the well, right? How can you essentially ensure that the hypotheses generated aren't being negatively impacted by maybe erroneous data that's generated by the LLMs? Does that question make sense? I don't know. It's like a raw idea for me.
So I'm a little bit confused as to when you say the erroneous dashboards, right? So your dashboards is capturing the wrong information.
Oh, I meant data, not dashboards itself.
Data coming from where, sorry?
From the LLMs, the output of the LLMs, going
Gotcha.
back into the input and creating a negative feedback loop.
Yeah, so I think that's where the tweaking is important, right? So if your LLM is generating results or metrics which have no relevance, like for example, it's hallucinating. So that kind of points back to the fact that were your prompts accurate, precise? Were they steering the LLM in the right way? Because garbage in, garbage out, right? So if your LLM is hallucinating and giving you some metrics which are nowhere on the dashboard or is telling you about a regional failure where you don't even have multi-region architecture, then something has gone haywire in the system prompt or the user prompt, right? So that's an indication of go back to your task board, design your prompts correctly, make sure that the dashboards are representative of the architecture you have in your architecture diagram. Otherwise, when you mix and match things like your dashboard and your architecture diagram don't meet, you could have results like the LLM could get confused. So there is a little bit of an onus on you to make sure that everything is mapping correctly. But this is where automation comes in, right? So if you're automating this entire process, there is less likely chance of doing something incorrect. Like you won't be taking a screenshot of a dashboard, which is not applicable to your application. But if you're doing it manually, you could potentially feed it the wrong file from the wrong folder. And that's where you will get the error.
Super fascinating. Thank you for sharing.
And I would also add that use the evaluation process. So we have not shown, in the interest of time, we have kept it brief, but we also have evaluation for LLM outputs. We're using like LLM as a judge. So that's another quality check on the data that it is producing.